understanding how a power attenuator actually works with your amplifier is a really difficult challenge. It's a very technical task. And a lot of the attenuators out there on the market don't do or understand any of that. They just go to the shop, see an 8 ohm resistor, and think, let's put that in a box. Instant attenuator, 8 ohm, moving on. And that kind of works. But some of the things I've seen are quite horrific. For example, if you buy certain power resistors, they have a power rating like 25 watt or 50 watt or whatever. And people think, great, a 50 watt resistor, throw it in a plastic box. It's like if you read the data sheet, nothing is ever that simple. Those are 50 watt at a certain room temperature with a certain size heatsink for a certain type of load at a specific frequency. And even then, there's got to be a certain movement of air. There's got to be all sorts of complicated stuff. And what you guys want as players, in my opinion, is to not care about any of that. You want to plug it in and go. And that's how we build our attenuators. I build them exactingly to the highest possible standards with the highest possible quality components. And we test the living oof out of them. Because, you know, you're going to plug these things into your precious gear and they have to be perfect, not some made up variable tweeter control in a box. So without further ado, I want to show you one of my test rigs, because this is the HotBox130, which is not yet launched. It's due very soon. This is pretty much the final version, and I'm just doing some temperature testing on it. I'm going to see if I can swap the camera around and you look at it. And you can have a proper look at it. So here we go. What we have here is the hotbox itself. It's very handmade, this version, without anything on here. And you can see here some of these big power resistors. These are 50 watts each. And we've got 4 of these in here. There's 200 watts worth of those alone, and I'm rating this attenuator at 130 watts or so. It gives you an idea that I know that this sort of size heatsink and this type of enclosure are suitable for that power rating. Theoretically, you could go higher, but it's going to get too hot. What each of these little transistor looking things here is a digital temperature sensor which has been bonded to the heatsink using thermal transfer tape. So that's the kind of tape you'd get on heatsinks in computers, and they're firmly attached to make sure all the heat is going into them, and these send digital information from various components which I've currently got them stuck on into this, which is a custom thermal load tester that I designed, which will log peak and current temperatures to I can't remember, it's a very fancy CPU processor system in there, and I can look and examine that data. In order to drive it, we run it off a 230 watt MOSFET amp that I can overload to death, and that in its turn is driven from a signal generator and an oscilloscope. And here you can see 2 scope lines. The flat one is the output. The spiky one is the input, which is there's nothing going because I haven't turned this up yet. So as I turn this up, I'm going to look at the screen and you'll see the power levels start to rise. So now we're starting to shunt power into the hotbox, and if I drive it as hard as possible, you might hear a little noise. You can see it clipping because that's the full 200 odd watts currently going in. So I'm going to back that off just a little bit. And over here now we will see with a little look. I shall ramp it up from. If we're lucky, we might see some of these temperatures start to rise because they're very cold. They're at room temperature at the moment. So we can see the left column, well, actually the peak as well, because I haven't driven most of them, starting to rise up. And we can see there that the bottom one is rising faster than the others. It's already up to 28 degrees. We can see the second one's rising at a moderate speed, which I'd expect 23 degrees. So I happen to know that the second one is this in the middle. These two are in parallel, so that's to be expected. They're the main load bearers. This one's rising a little bit faster than I'd like it to, but it's well within parameters. These things can hit 100 degrees safely. And of course, we're putting nearly full power into this thing at the moment. Let's get it just spot on. So there we go. We're 100, that'll be about 120 watts. I've just adjusted it for 120 watts. So I'm sticking 120 watts in, so it's in the ballpark. And yeah, we can see the temperature's rising. I'm not entirely surprised about this one here. It is actually a very important resistor in the chain, and it's the second dropper, if you like. The first dropper takes the load. Oh, there's a sort of a click there, a little click noise. That's temperature building, I'm guessing, things moving. And I'm now going to watch this over the next half an hour and poke and tweak. And I'd move the temperature sensors to other areas later, but I know these are the important ones to begin with. I know these two aren't currently in use. They're to do with different reactive settings. That one's an important one. Helps set the filter frequency for the inductor, which is part of the reactive network. This one without one on is also quite important, but I'm not as worried about that as this one. So there we go. I'm going to watch all that and see where we get to. You see the amps there's pumping overload out of its simple VU meter. And there we go. And I will do different signals and square waves and different stuff, and I'll watch this to death. So yeah, always have confidence in what we do. 100% point to point, top end components, British made where we think that's the best. And if we don't think that's the best, we'll go somewhere else. Yeah, Nutric jacks, and yeah, very thorough design and test process. Thank you for watching.